What is up, mathletes? So today we're going to talk about adding and subtracting radical expressions. So let's make this easy, all right? So let's talk about something we're already familiar with, which are these like terms, right? So we know like terms have the same variable factor. So here I give you an example of 7x and 6x, right? They both have the same variable and they both have an exponent of 1. So they have to have the same variable, same exponent. So when we talk about like radicals, it's really the same idea. So that's nice. So we don't have to get all confused, right? So for like radicals, we need the same indices, right? So the same index. And so right now my index for each one of these is 2 because we're taking the square root, and the same radicands. So whatever is inside of the square root has to be the same too. So that's what's meant when they say radicands. And what's nice is I'm going to be able to add these and I'm going to be able to subtract these. So for example, if I were to go ahead and add 7x plus 6x, we know we have a total of 13 x's, right? And for our radicals here, we have 7 square root of 11, and let's go ahead and add 6 square root of 11. So here's a way you could think about it that might help you out. How many square roots of 11 do I have here? Well, I have 7. How many square roots of 11 do I have here? I have 6 of them. So in total, how many square roots of 11, right? How many square roots of 11 do we have in total? Well, we have 13 of them. So just like we did before, right? That's one way to think about it. We add the coefficients, right? And our square root of 11 stays exactly the same. So that's the mentality I want you to have as you're working through these radicals, so you don't get so confused. All right, so let's take a look in here and let's see what else we got. All right. So how do I add and subtract these radicals? Well, first of all, right, what's nice about these examples that I'm providing for you, especially the first one, is note you always want the radicals to be the same. You could only combine like radicals. So I'm going to be able to actually add these because they both have the same, these radicals have the same index, right? They both have an index of 2. And the radicand, what's on the inside, is also a 2. So don't let that that 2 confuse you. It could have been a little 3. So they have to have the same base and they have to have the same radicand, what's on the inside. All right, so let's go ahead and tackle this. So again, our answer is still going to have the square root of 2, but now I just add the coefficients, the 7 and the 8. So we get a total of 15. All right, let's do another. So here, let me go ahead and identify which one of these are like radicals. So let's look at part B here. So this has the cube root of 5, all right? This one has a cube root of 5, but check this out. There's an x on the outside. So 1, right, this has a coefficient of 1 minus 4x. Well, I'm not gonna be able to combine those because those aren't like terms. All right, let's check out this one over here. I have the 6th root, right? So actually, for this one, there is nothing we could do. And what we would say, our answer would remain the same, but these are not like radicals. These are not like radicals. So that I just leave exactly the same there. All right, let's go ahead and let's look at this piece right here. So, I see a little, let's go ahead and let's put a plus. All right, let's add the last piece. We're gonna go ahead and we're gonna add that. All right, so let's look at these pieces here. So I have the 6th root of 5x, all right, and I have a 5 on the outside and, an 8 on the outside and a 5 here. So these are like radicals. So I'm gonna be able to work with these. So let me underline them. And then here, for this last term, I have the cube root because my index is 3. So because the index is different than these indices, right, I'm not going to be able to do anything with this one. So this one, I'm just going to drop it on down. So let's go ahead and combine these. So 8 minus 5, that gives me 3. And remember, the radical is going to stay exactly the same. It's going to have the same index, which was 6, and then the same radicand, which is just what's on the inside. So that stays exactly the same. All right, so those two, we combine them, and that's what we got. And notice what we said, this is not a like radical. So I can't do anything with that. So we're just going to drop it down. So plus 4 cube root of 5x. All right, so that's what we are left with there. Excellent. Let's move on. All right, so just to make sure this makes sense, we have a checkpoint for you. So what we want you to do is you go ahead and try these out based on the lecture we just looked at and comment down below. We still have more to talk about, but right now, before you forget, right, practice this, press pause before we move on, practice this, and then let us know down below in the comments. Tell us what you got. All right, so let's continue the march here. All right, so simplify by combining like radicals, if possible. Well, right off the bat, this is where I tell people to be careful, because right off the bat, people are like, well, wait, I have the square root of 18 here, and I have the square root of 8 there. So if you haven't checked out our other video, we linked it down below, of how to simplify radicals, because your first job is to simplify each radical as much as possible. So let me show you. So the 7, we bring it on down, but the 18, we're gonna break up the 18. All right, and then the 8 over here, that's our radicand, we're gonna break the 8 up as well. And notice how I break it up. And so if you watch our other video, what we said was we need two numbers that are gonna be multiplied to give me 18. But the first number has to be the greatest perfect square. So what we said was 9 times 2. And you want the 9 to be here because we know the square root of 9. It's just 3. And likewise, when we have 8 here, we're going to break it up into 4 times 2 because 4 is the largest perfect square. So let's go ahead and let's simplify this. So you're left with 7. We know the square root of 9. That's just 3. And the square root of 2, we don't know, so we just drop it on down. Perfect. All right. Plus 5, the square root of 4, we know that's just 2. And then we drop down the square root of 2. All right. So let's clean this up. Let's go ahead and do the multiplication, right? So we're going to multiply the 7 times the 3, and we're going to multiply the 5 times the 2. So cleaning things up, we're left with 21 square root of 2 plus 10 square root of 2. So in this first piece, how many square roots of 2 do I have? I have 21 of them. In the second term, how many square roots of 2 do I have? I have 10 of them. So in total, right, that's the logic, that's the thinking that I want you to have. You have 31 of those square roots of 2's. So this is our final answer. We were able to combine them again because they have the same index and the same radicand, which is on the inside. All right, let's look at question B. All right, so same idea, right? So 4, we're gonna break down that 27x. Oh, but notice we have a variable. The rules don't change when you have a variable, so that's great. And then we have 8, and then we're gonna break up that 12x. All right, so 27, we look at our list of perfect squares, and we notice 27, I could divide that by 9, right? Because 9 is a perfect square. So 9 times what is 27? Well, 9 times 3. And x, I'm going to throw that in there because I do not know the square root of x. And we're going to get some examples later to help illustrate, well, when do I know I could break it down, that I could take something out of the radical? All right, be patient, we'll get there. All right, the square root of 12, Well, when I break up 12, that's just 4 times 3, and then again the x is going to go in there because I can't take anything out of the square root there. So continuing, we're left with 4. The square root of 9 we know is 3, and whatever you take out of the square root you multiply by whatever's outside. Okay, so we're left with 3 square root of 3x minus 8. The square root of 4 is 2, and then we drop down the square root of 3x. So again, our goal, hopefully what we're starting to see, is that these radicals are like radicals. They're the same, all right? Because when they are the same, then I'm going to be able to combine them. So we're left with 12 square root of 3x minus 16 square root of 3x. So there we have like radicals. So now we just work with those coefficients, the 12 minus the 16, which leaves us with negative 4 square root of 3x. So there you have it. Bam. All right, and last portion for this section here, we have 7 square root of 3. So I look at that square root of 3. Can we break it up? Nope. And then I look at that square root of 5. Am I going to be able to break that up? Nope. So in fact, these are not like radicals, and you cannot you cannot break down that 3 and that 5, right? They're prime numbers. So our final answer here, there's nothing we could do. There's our final answer. We cannot combine those radicals because they are not like radicals. All right. So for that last section, here's the 3 problems we want you to practice again to make sure you have a good understanding, right? Because it might make sense, but you have to make errors yourself, and you have to work through this to make sure that you actually do have it, right? So make sure you try these 3 problems, 4, 5, and 6, and again, comment down below, and let's see if we're getting the same answers here. All right, so there's our second checkpoint group. Let's continue. For the grand finale. All right, so notice adding and subtracting with higher indices. So now what happens when I leave square roots? What happens when I talk about cube roots, fourth roots, fifth roots? The idea never changes. So because in this example, I'm look at my index. My index is 3. So what that tells me is that I'm gonna need perfect cubes, right? When I'm breaking these numbers down. All right, that's a huge piece of it. All right, let's dive in here. Let's take a look. So we're left with 2, and notice we're gonna break this up like we're used to. And we have 2 there, and then we have 4, and then I'm gonna have 2 there. In the first radical, what I always say is put the largest, right? The biggest perfect, in this case, the largest perfect cube. All right, so 16. What's the biggest number here that I could divide by 16? Let me do some math. Good. 8. So 8 times 2. And now let's look at that 54, right? What 2 numbers are we going to break 54 in? And remember, the first number has to come from this list. So let me do some math here. Excellent. So 54 is 27 times 2, right? And make a note, these numbers right here, they have to come from this list of perfect cubes, all right? If not, can't do it, all right? That's as far as it goes. We can't break it up, right? Because it doesn't help us to do, say, a lot of people say, why can't I use 4 times 4? Because if you have a 4 in here, we do not know the cube root of 4, right? So that's why we need to use this list. Because here, I know the cube root of 8. The cube root of 8 is 2. I know the cube root of 27. The cube root of 27 is 3, right? We could simplify this. All right, so let's do it. So we end up with 2 times 2, right? That's what the cube root of 8 is. And the last factor we leave inside of the radical, all right? Likewise, we have 4 times 3 cube root of 2. So just like we did before, the process never changes. You have to be able to simplify first. Then you could ask yourself, after I've simplified completely, do I have like radicals? So we are left with 4 cube root of 2 minus 12 cube root of 2. So 4 minus 12, that just leaves us with negative 8. And the reason I combine them is because look, they have the same radical. Same index of 3, same radicand of 2. So therefore, I can combine these. These are like radicals. All right, cool. So now for this piece right here. All right, let's look at this one. This looks funny because now, wait, what do I do when we have variables? So listen closely. When you have variables, what you do with your exponents is you divide them by your index. In this case, your index is 3, right? Here, if I have 1, I can't divide 1 by 3. So 2, I can't divide 2 by 3. So this first term here, we're going to leave it the way it is, right? And it's going to make a lot more sense once we jump into the second term. So this one, I'm going to leave it. And the second term, right? This one I am going to be able to factor, to separate here. So let's start with the number portion. 8. 8 is already actually on this list. 8 is a perfect cube. So 8, let's go ahead and we leave it here. But x to the 4th, well, I can't divide I can't divide that exponent by 3. So what we do is, just like we did before, we separate it. So this is the same thing. X to the 4th, that's really the same thing as x cubed times x. So here comes the big question. Why? Why did we do that? Well, first of all, let me ask you this. Here, how many x's do I have? 3 being multiplied, right? Here I just have 1. So in total, I have 4 x's. So if I multiply these two, I get the original. All right, so I haven't changed the math, but the reason why I did this is because look what I said. We're gonna take that exponent and I wanna make sure it's divisible by the index. So can I now divide this exponent by 3? Absolutely. So we broke it up. You keep looking for the next smaller number until you could divide that number by the index. Same thing happens with the y to the 5th. What you wanna do is, the 5, obviously, you can't divide by 3. So you keep going down. 4, can you divide the 4 by 3? No. 3, can you divide 3 by 3? Yes. So the y to the 5th, let me write that a little nicer. Y to the 5th, I'm going to keep breaking it down until I get an exponent that I can divide by the index. So now I have 3. That's going to be divisible by 3, right? So here I had 5 y's, right? Y times y times y times y times y. And here I factored out 3 of them. So that means over here, I better have 2 of them left, all right? So this is gonna help us simplify. So whenever you have exponents, that's how we simplify them. All right, let's continue. So now we have 5 cube root of xy squared plus, and here is the work. Well, what's the cube root of 8? The cube root of 8 we know is 2. And what did we say to do with each one of those exponents right here? We said divide them by the index. So we're left with x to the first power. I don't need to write that one. Y to the first power, but just so you remember in your notes how you got that one. And then you're left with the cube root of xy squared. So make sure it's very clear in your notes how you went from here to here. All we did is we divided the exponents, whatever they may be, by 3. All right, now we ask ourselves, okay, can I combine these? Are these like radicals? Well, they have the same index, they have the same radicand, but look on the outside here. I have 2xy. Look on the outside here. I have 5. Those I cannot combine. So we are finished. That's as far as we could go, folks. All right, so time to make sure that you really understand what the heck just happened. So we have 2 more checkpoint problems, and these I want you to wrestle with, right? Take some time and then comment down below, what did you get? We're interested. All right, folks, so this idea, it's a little bit more complicated, but give yourself time and comment down below. We want to hear your thoughts. And if you want to see more videos, let us know. We'll talk to you next time. Peace.